start at 8:10. I waffle back and forth between 8:05 and 8:10. And every time at 8:05 people come strolling in late, and then at 8:10 it seems so long to wait. Looking around, I know most of you, but not all of you. I'm Carol Little. I'm the math coordinator. I do these sessions for parents, first grade through fifth grade, on their major number sense units. I don't do geometry, I don't do shapes, those are pretty hands-on. And then I do yearly ones for KG and pre-K, where they're still developing. This unit is a follow-up on the unit before where they went to 20. But with 20, they emphasized place value, but it didn't mean as much because you only had up to 10 and then 11 to, or it's actually 0 to 9 and then 10 to 20. So in this unit, the idea of place value becomes very important. And they'll be playing a lot with the numbers. So the number 11 can be 1 10 and 1 1. It can also be 11 ones. So this idea that a number can be broken apart in many different ways is really essential. And so we're going to be using a lot of number bonds to represent the numbers. On the first page, there's vocabulary. We use this vocabulary with kids. Good morning. They're not expected to memorize it, but we use it with them, and we often use explanations with it. But by now, we've been using compose and decompose since kindergarten, and maybe even pre-K. A lot of the kids know it, but we also talk about taking it apart and putting it back together. Place value, this is the time where that language starts coming in a lot. It's the idea that the ones can be bundled together and put together as a 10. And in our system, which I am pretty sure it's used around the world, when you have 10 of something, you need to go to the next place value up. So 10 ones can become 110, 10 tens becomes 100. They're not going to the hundreds, that's second grade, but it's starting to learn that pattern. Unit form, I'm giving you this language, just how we break apart and talk about numbers. Addition sentence is the kid-friendly language for equation. We would use both that, and sometimes you might see it as an addition sentence. That one I hope not as much, but we definitely still use the term, well, it says addition sentence or number sentence. Make 10. I am actually trying to slide this language out a little bit to make a friendly number. 10 happens to be our most friendly number at this point. It was 5 in kindergarten. The reason I'm switching the language a little is because when you're adding 17 and 20, or not going to come up with a good one. Some kids want to go back to the word 10, and 10 is below it. We meant the tens place is how that came into the idea, so they're only talking about the ones place. But if we talk about making 10 or making a friendly number, it's about that ones place getting to the tens. In second grade, it will be about the tens place getting to the hundreds. But it's really multiple of tens, but that language will be in there. This is a big unit on greater than, less than, and equal to. And they will need to prove their work. So we want to see if they understand if a number is greater than another number. We also want to see if they can understand the symbol that goes with it. Because sometimes they understand the concept and they're just lagging behind on the symbol. And that's a lot easier to teach. If they don't understand that 32 is greater than 12, that's kind of a big thing, and we've got to go back to the manipulatives versus which way the alligator mouth goes. Number bonds, they've been working with a lot. We will continue to show this representation. It's just how a number can be put and taken apart. What I do want to also make sure is it doesn't have to only have 2 parts. We talked about this as part, whole. It can be part, whole. So it's just a little something to know. This is what the place value chart looks like in our first grade. If I were to draw it, I would draw it like that. I don't have to fill in all the outer area. But I would label it. I don't know. I don't think your kids are I think you're always being given the chart. I'm used to teaching older kids where I would definitely accept a T and an O. But when we're first learning it, that's too abstract. It would need to be 10s and 1s. Quick 10. I'm just going to be real obvious about this. This is really going to become the go-to for most of the kids. It's a way to represent the manipulatives that they've drawn in a quick and efficient manner. We'll talk about arrow notation. And this is the tape diagram. The tape diagram is used a lot to explain what's going on in a word problem. We absolutely require the kids be able to make a visual representation of what's going on in word problems. In first grade, they'll probably also use it to solve the problem. As they get older, they will continue to use the tape diagram, but it's really to make sense of the question, and then they'll have to go do the arithmetic down below. Okay, and I was talking to you walking down here. Really, you do know how to do this math. But how is it being represented? These are what might be new to you. I do want to show you these number bonds. All of a sudden are squares. Number bonds are not written in stone how they have to be. They can go sideways. They can go upside down. It is the relationship between part, whole. The whole is always going to be one that the parts come out from. So we're looking at this. We have 10 grapes here, 10 grapes here, so we have 20 of them. We have 7 more, so I have a total of 27. I could have counted 10, 20, 21, 22, 23, 24, 25, 26, 27 and written that first, and then figured out that the other part was 7. Kids are going to do it amazingly different ways. In this unit, you'll see that the bundles are supposed to be obvious. I may have had kids who didn't notice that on grapes, but we would talk about that a lot. Obviously, the peanuts are bundled in bags. Most kids at this point are still going to double check it and count it. I can guarantee you there's 10 in there, and that's what the kids will start seeing, and they'll start going, oh, I can assume that. So 10, 20, 30, 32. So this is just a lot of the numbers getting bigger than what they used to be. I want to skip down. You can see these are the same, although let's go to this one. They've separated the 10s because this problem really is a setup of 18 plus 21. They would have built it. So now they've got an answer of 10, 20, 30. I've got 30, and I've got 5, 8, 9 ones, so my total is 39. And I guarantee you, every time I do this one, a child can do it a different way, and that's okay that we all end up at the same spot. Whether they're seeing the parts and going to the whole, or whether they're figuring out the whole and going to the parts. I put a lot of problems on here for you to see. If you want me to do one that I skip, I'll be glad to. But I know ones that I really want to point out. And I'd like to get down to these bracelets or necklaces. Let's have necklaces. Because this is where we're starting to talk about that flexibility of seeing them as 10s and 1s or just 1s. I have 2 10s and 4 1s. If my necklaces were to break, that is the same as 24 ones. This is a key concept. And then the notation. This box, we have 27. How many 10s are there going to be? 2 with 7 ones, and that is the same as 27 ones. I want you to look at the last one. We have been taught, I personally would have written this as 20 plus 5. We want to make sure that they are seeing it both ways, that we don't always put the double digit first and then the single digit. Because in real life, if there's context to it, that's not necessarily. I mean, if I bought 5 apples first and then went to the next vendor that bought 20 apples, the number sentence really is 5 plus 20. Now we know they're interchangeable in how to solve it, because addition and multiplication, the order of the numbers don't matter. But we want to make sure they keep seeing it multiple ways, and that they might see it like this. The interesting thing is, we're good at practicing this in first grade, they see it a little bit less in second grade, they see it even less in third grade. By fifth grade, they look at this and freak out. I was like, no, just stop and think. Because they see it so often in written materials. Not in mathematics, not in the real world, but in what we give them. Greater than, less than. This is a big thing. So we will be building a lot. I do have the cubes out there for you to see. We'll be using tens where they'll get these built in tens and kind of leave them this way. But if we have the number 34, this is what's going to happen. I'm not going to have enough cubes. Oh, almost. I'm first going to build it. I have 3 tens and I have 4 ones. It then says 20 and 4. So first of all, we're just going to talk about the value of the number. Which one is the greater number? We use greater. You can use bigger than. Just mathematically, it's usually greater. We'll probably keep saying it, but we're not. Bigger than is correct. We'll accept it. So which one is greater? That's your question. It's 34. And then I'm going to say, how do you know? Yeah, it's 10 more. We're going to say, then show that to me. We're really going to get them to be able to explain it and show it to me. Because if I take one of these away, I now have the same amount. I have 1 extra 10. I mean, there's a lot of ways of saying it, but we want them to be able to explain that thinking. We've now built this. The next step, while this is out in front of them, would be to draw the quick tens. What we mean by quick 10 literally comes from we can draw it quickly. Oh, and I'm sorry, that was 5. I had covered it up with my cubes. Didn't change the answer. So we can draw it with quick 10s. We can now start making comparisons. I know that this is 34. I know that this is 25. And then we start off with the language. So 34 is greater than 25. We do give them words, word banks, is greater than, is less than, is equal to, so that they understand the language that we're looking for, because it is particular language. So where it first starts off is, what is the value of this one? 20. And, oh, it says it right there, 18. Okay. So now I'm going to do, is 20 less than or greater than or equal to?
Great.
Now, up here, they said we could use letters. We don't go very far down that route. We go from the words to the symbol, but we're not trying to torture the kids by making them right. We want to make sure they're understanding what's going on. 2 tens and 3 tens. I am going to make them draw it. So 2 tens would be less than, and it uses the L. I don't have an equal than on here. And again, each time I would be asking, why is it less than? Why is it greater than? And with the picture there, they can say, oh, there's one more 10 than there is in here. The 24 is greater than. So we are setting up the language to match the symbols. Then we get to this alligator mouth. It's funny because as a mathematician, I'm not overly fond of it, except that I can remember the alligator from elementary, and it worked for me. I'm like, so what's the matter with it? There's a problem with it if they don't understand what's going on. I think the alligator math really is just to remember which symbol. I have to know whether it's greater than or less than, then I just have to match the right symbol. The idea is that the open mouth is always towards the bigger number. I've also seen, let's do 8 and 10, where they draw dots, and wherever there's more dots on this side, so it should go to the larger number. So at this point, we are just trying to help them memorize the symbol that somebody made up a long time ago. And that's fine, whatever way they can do it. But the large open side goes to the large number, the more dots goes to the bigger number. Anyway, they can talk about it. In this program that we use, I mean, most of the worksheets, they will be seeing that alligator mouth. But they're going to have to prove it to us still, because otherwise it can become a guessing game. I can finish my homework real quickly. I can just do any symbol I want and be done. No, we need to see the reason why. So 27 is less than 24. So less than, 27 is greater, my open end has to go there. And on this one, I think they're just writing the same thing. Nope, they're writing it, sorry. So they're trying to make that connection a lot between the language and the symbol. But I haven't proven anything here. Originally, I should have written 24, and then I would be able to say, oh, it has fewer ones. It has the same number of tens and fewer ones. 31 is also greater than. So you can see how that goes. The symbol really is the bigger hang-up than the understanding of numbers. Because really in first grade, even though the numbers have gotten larger, they do understand the idea of numbers that are bigger and smaller. And you can see where I said the quick tens, this becomes the easiest explanation. They could write it out. I really can't imagine a child who would do that, but they could write in words, there's one more 10 and that. We would accept that. We really do want to know their reasoning. This is just really clear. I do want to talk to you about when they start drawing the ones. I am a big proponent that by the time you get to the ones, you draw them a 5, and they always draw them up and down, vertically instead of horizontally. This is just really fast. I know by looking at this, especially if I drew it, that that's 7. Because as soon as I get to 5, I follow the old 10 frame thing and I go up and I put my next 2 in. Visually, I can see that and I don't have to count. If I were to put 7 dots in a row, the brain really has a hard time seeing past 6. So this is an organizational thing. I'm going to suggest it, and I'm going to do this over and over again. If a child insists on doing them 7 in a row and keeps getting it right and doesn't want to follow my way, I'm going to let them because they're succeeding. More likely, theirs are all over the place, and we need to get them back into organization. Most kids will follow, honestly, what the teacher does. And I can't guarantee that all teachers are doing it that way. But if your child is struggling with that accuracy problem and not being able to follow their work, this is a really strong thing to do with them. Get them organizing into 5s. So you can imagine by 29, even drawing the 29, can you see, is going to get, they're going to take up more space, and that's just where things get messed up. Maybe they'll only do 29. Where my brain, I've used 10 frames a lot, and your kids have used 10 frames a lot, should be able to see that that's 9. So they'll work on greater than, less than for probably a couple of weeks. I'm telling you, I'm going through this very quickly. This is a 7-week unit for your kids. Please do not go home and try to teach all this tonight. Trying to get kids ahead can cause 2 different things. One, just that little bit of difference in us putting our spin on it can confuse kids. And if you teach ahead, it really will instill some not wanting to pay attention in class because they've already seen it. And that way we don't get the conversation out of them and we don't get to hear what they're doing. So if you're trying to enrich your child's math life, we'll talk about that at the end. There are a lot of other things that we could be doing, not just getting them a couple days ahead. Okay, 19 and 10. This is the beginning of the addition part. This is where we want them to start thinking about adding a unit of 10, not counting up 10 ones. So what do I mean by that? If I have 19, I could go 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. It will work, guarantee it. Or now that I understand this idea of about 10, I could just add one more 10 and I get 29. So this is where efficiency comes in and it becomes accuracy, and this is showing that the kids really understand place value. So the beginning of this addition part is about adding tens. We'll have lots of other weird numbers for their add end, but what we're adding to it or have will be some sort of multiple of 10. So this is also showing what the part whole looks like. I have to figure out 29, and I now know it's two tens and 9 ones. The reason for all this representation is to show the linking and how they're not competing against each other, they're actually all showing the same thing. So 20 and 14, if I draw the 14, 20 is how many tens? 2.
2 tens.
So I can add that to it, which is a lot more efficient than counting up 20. So although we allow counting on our fingers, we do start showing them how it becomes, or we grow out of it because the numbers are too big. So now I can see that my 20 and my 14 go together. My whole is 34. I ended up with 3 tens and 4 ones. Now you can see after some practice, there are going to be kids who can look at this and say, oh, I'm adding 2 tens. That would make it 3 tens and 4 ones. This is the scaffolding to be able to see it and understand it, and then we move on to the numbers because they're ready and they're flexible enough in their thinking. Which leads to our next way of writing it, where this is a bit of an approach for mental math. Can they just add it in their head? And this is a way of being able to show it. This is what I'm doing in my head. This is how I can write it down. So if I have 13, I can add 10, and I get 23. If I had 19, and I jumped to 39, what happened? Well, my 1 stayed the same, but my tens went up by 2 tens. 2 tens means I had to have added 2 tens, which is 20. If I don't know what I had, and it went up 10 and I got to 27, it had to be 1 10 less. It has to be 17. And that would be 18. This arrow way or arrow notation is being introduced here. Some kids love it. Other kids will begin to see its use as the problems get more complicated. But when we're introducing something new, we want to take them back to the math that they already know. So they should be able to do the plus 10 and minus 10 when we do this. It's the notation that we're teaching here. We will never, ever, on an assessment, say you have to do the arrow way. We will in the middle of the unit because we want them to practice it. You know, we know you know this way, now let's try this one, because if you don't practice it, you're never going to come to like it. But on an assessment, they're going to get to solve it however they want. And then we get to the heart of the heart of this unit is the place value, and then the adding any 2 add-ins up to within 40. So we've done the adding tens, now we're getting to funny numbers. And this is where we're going to go back. We're changing concepts. What are we starting with? We're starting with 22. I'm going to have them build it first. I do like the picture here. In my classroom, I would have all these sticks one color, so that if you had 22, these might be 22 blue, and then you could see the 6 orange being added to it. I don't have the luxury of having that many manipulatives for you to be able to do that, which is too bad, because then you can really see the difference. I wonder if I have 6 black. I do. We are trying to make it as visual as possible. So if they started off with their 22, we added 6 more on, I now have my whole. There will be a few children who start here and count. They'll count 10, 11, 12, 13, 20, 21, 22, 23, 24, 25, 26. Most kids will start with the 20 at the beginning and then count up. What we're really hoping to is that they get to 20, they hold the 22 and then count on 23, 24, 25, 26, 27, 28. So that's the progression of understanding. And then we will get to the kids who can start seeing, well, my 1s, I added 2 and 6, and that's a fact I know. I say that. First graders are expected to know their math facts to 10 by the end of the year. So this math fact they may or may not know. It might depend which one, it's going to depend on the child, it's also going to depend on which fact it is. I mean, the +1s, they're there. +2s, I don't know. That's going to be an individual thing for kids. But we have it with the manipulatives. We're going to teach them how to draw it, and they are welcome to be counting. They're just going to get more sophisticated in their counting as they practice. So I can see that there are 2 10s. There's 2, 3, 4, 5, 6, 7, 8 1s. So my answer is 28. I do want to show you this drawing. This is 14 plus 3, and we would in class be doing something like this where you can see what was the first addend and what was the second. So they used dots and then X's. That's pretty typical. Some child might use 2 different colors, whatever, but we want to see what the 2 different numbers were that were being added together.
14 or 24?
Oh, thank you. I was so worried about the 4 and the 3 that I didn't look at the 10s. You know, I say this, I've never done one of these without making that sort of mistake. These are the type of things we really need to listen to, because I do actually understand how to add 24 plus 3. I've just made simple, that's a careless error. We don't want careless errors, but they're real and they happen. How I address somebody with a careless error is very different than how I address a child who doesn't understand the concept.
Oh, like my child does have careless error, and I remember when I was a child, I would understand, but when it comes to assessment, I just do errors. I have no idea how it happened.
And you're sitting here today perfectly fine in math. I mean, we don't want careless errors. Some of it's just maturity, and some of it's when they have to keep going back and redoing it. Because if I had that child in my class and this sheet came up and there's 2 out of 3 wrong, I'm not going to tell them which 2 out of 3. I'm going to say, got some wrong, go try it again. So it's really getting to them to slow down. And if I tell them which ones are wrong, that's kind of an easy guess. If I was that careless kid, I'm like, yeah, I'm just going to go for it. But now they actually have to rework all 6 because they don't know which ones and they don't know how many are wrong. So it's kind of instilling that idea that maybe counting twice is a good idea. We will talk about solving problems 2 different ways to prove their answers correct. Yeah, and I hate to say it, it commonly is boys, not girls, but not much. we can still make it, and it's a habit of mind. And it's probably not just in math. They're probably doing it in spelling. They're probably doing it everywhere. So it's take a deep breath and keep working with them. But we don't want to beat them up and make them hate math over a personality thing. But I would make them redo the work. And I'll tell them, I want my doctor putting the right amount of medicine into that shot. I don't want my doctor being careless. So I don't want my engineer I talk about my brother who's the engineer. my brother and I went to the same university, and he was getting his master's in engineering, and I was getting a BA in social sciences. Guess who got the job first? He's sitting in an oral presentation where he looks down and he realizes he's designed a building that's 5 stories high, and his elevator goes to 20. There's problems. In real life, you have to be accurate. He failed that oral exam. So, you know, there's the practicality, but a 6-year-old's not going to care about that explanation yet. They're going, I hate to say it, they're going to care more that they're not moving on to the next thing. So if we just teach them that slowing down to begin with will actually get you there faster, that's what they're going to listen to more. But the big deal is don't tell them which one's wrong, make them relook at all of them. Okay, so this would be 12 plus 1, 2, 3, 4, 5, 6, which would be 18, wanting to make sure they recognize that as 1 10 and 8 ones. This place value chart is really there to keep them thinking about how numbers are built. It's not helping them solve the problem at all, but we want to make these connections between numbers as often as we can. And then we're going to have them draw them. Now they go up all the way to 10. I guess with this you could, I still might do it in 2 rows. They're both correct. I can't mark a kid right or wrong because of it. But again, manual dexterity in 1st grade can be a big deal. I'm going to take a look at the child's work and see what might work for them best. Now, I always, when things get to 10, I always have them circle it. Because that's that idea, that's the new bundle. That's what kicks it over into the next place value. Which I can also see why I will bet they have them draw it in 1 strand, because then it's going to look like a 10. 5, 6. And they either circle it or they draw a line through it. I mean, both of them are signaling the same thing, so that they end up with 3 10s and 0 1s. And strangely enough, the 0 1s can be a sticking point. That idea of making sure that there's a 0 is an important part of this. Yeah, and so this is showing this same thing. We are now adding, we call it going across a decade. You don't need to know that language, but that's the easiest way for us, meaning that you're getting to that next group of 10. So if we have 15 and 5 more, I got ahead of me on the last page myself. Here's our next 10, so I have 2 10s and 0 1s. 15, I've got my 6, so I have 2 10s and 1 1. Yeah, I think I better take back, I think I better do it in a single line. Okay, that would be a whole 10. I have 30 and 2. So you can see the progression. Went from adding 10 to adding numbers that didn't go across a decade, or shouldn't have, and then they're going to go across that decade. This will be the sticking point also, not when they're drawing it, it's when they take their drawings away. I really want to talk about these visual representations. They will be doing these through calculus. It's not about outgrowing them in 1st or 2nd grade. It has nothing to do with being smart or not smart. It has to do with being able to see the math. And this is a way of proof. So if a child has already learned how to do these mentally, I'm still going to ask for proof. I want to know, I mean, just because you tell me it's 20, why does that make it 20? It makes it 20. And we do ask for proof. I wanted to get to the word problems. And these are where we do require them to draw some sort of model that shows they understand what the question is. Tape diagrams work really, really well. Tape diagrams are really a linear, rectangular model of a number bond, often. So we will start moving away from number bonds, mostly because the tape diagram works for so many things. So here, Lee saw 6 squashes and 7 pumpkins growing in his garden. How many vegetables did he see growing in his garden? So with a tape diagram, I try to get them to draw this as big as they can, just so that things in there fit easier. So my first thing I have is 6 squashes. I'm going to draw 1, 2, 3, 4, 5, 6. So that's one of my groups. That's part of what I have. And then I had 7 pumpkins. 1, 2, 3, 4. Now, I think there are probably some kids that will have read this and say, oh, I need 2 parts. Whether they draw it in by squash first and then pumpkins and put the partition, or they put the partition in, I don't care. The only reality is this number might have been 42, and it would have been hard to fit in there, but I doubt it, because by the time we get to that big, it doesn't make sense to be drawing all those little things anyway, and we'd use the number. So it really doesn't matter. I think to begin with, most of them would draw the dots for squash, and then put a partition, and they're not going to use that word, put a line, and then draw the pumpkins next.
So here it's not important to group them into 5s for visual.
No, I think they're not going to. They're going to go 10 across. And it's fine if they do. I think they're going to see it this way, and what they're going to do is now is they're going to come to, well, let me finish. Because this, if I were to look at this as somebody who hadn't read the problem, I don't know what's going on. In a word problem, or what we call a real life problem, we want to know. So they're going to have to label this squash and pumpkins. And then I want to know what the total is. I don't know, so I put a question mark. That's what I'm solving for. And I think what they're going to do now is, we've got 6, how many does it take to make that 10? And they're either going to circle it or put the line through it to show a quick 10. So they've now used the drawing to help them solve it. Very, very common in first grade. As I said, as we get older, the tape diagram just helps us understand what the problem is, and then we have to go do the work someplace else. But I now know that I have 10 and 3 more, so I have 13 vegetables. At this time of year, this sentence is probably not, excuse me, not being given to them. They should know that they have to write the math sentence at the end of the problem. And the main reason is, this question could have been how many more pumpkins were there than squash. By having to go back and remember the question to write down the answer, you are double checking that you're actually answering the correct question. I do want to show, and this is that some people do, so this is the part, and this is the whole. It doesn't matter, we're not trying to make them into little robots that each one of these look alike. So both of those representations work. And the truth is, if you go on the internet, you will see it both ways. There isn't one predominantly favored over the other. But a child could also do this. Now they have to label it, and I know that at this point they want them writing out the words. I just don't have a lot of space there because I've done it 3 different ways. This represents the question quite well. It doesn't overly help them solve it. But they understand what to do, so now they can solve it by drawing quick, well, they don't quick 10s because it's too small. Where this one, if they draw it this way, they have the representation to also solve it. So that's also why we kind of go this way. Does that make sense? Mm-hmm. Okay, so the next one. Kiana caught 6 lizards. Her brother caught 6 snakes. How many reptiles do they have in all? So what's our, we've got our tape diagram. this was lizards and snakes. How many reptiles? You can see I'm a favor. I got started with the 2 lines as opposed to the box. I don't mean to favor, it's just my habit. And now I can do, now this is interesting. I may look for a 10 and a 2, but they've also learned their doubles. So if they know 6 plus 6 equals 12, that's fine. We're not trying to make them go back and undo what they already know to show it to us. If it's within the realm of their knowing it. I know they've learned their doubles, so I would totally accept that. Yeah, I'm not real sure. And up here, I'm sorry, they probably would expect to see 6 plus 7 equals 13, the number sentence. There were 9 dogs were playing in a park. Some dogs came to the park, then there were 11 dogs. Different story. I have parts. I know there were 9. How many joined them? Do we know? It says some. Some means I don't know. There's my question. And then I had a total of 11. So I have dogs, I have joined, and I have my total dogs. So if I have 9, I need to count up. I've got 10 and 11. It means that 2 joined. The very vast majority of kids, because the way this story was written, will what we call add up to get to this answer, because that's what's happening. That's the mind movie that you're making. Is this also a subtraction problem? Yes, to those of us who see it, who have a lot more experience in math. This could also be 11 minus 9 equals 2. I think at this point in first grade, unless you've been doing extra work, a child's not going to naturally see it that way. And I would argue that this follows the story better. And mathematics is about explaining the real world. I would accept either. We want them to get to this flexibility. It would be surprising right now. So now, 16 strawberries in a basket for Peter and Julio. Peter eats 8 of them. How many are there for Julio? So now we're starting with the total. So I'm going to draw all of them. 1, 2, 3, 4, 10, 11, 15, 16. I have my total. What happened? Somebody ate. Peter ate 8 of them. I'm going to cross them out. 3, 4, 5, 6, 7, 8. So here are my now 2 parts. We have what Peter ate and what's left for Julio. This is now a classic takeaway problem. We had 16. I took away 8. How many do I have left? And I probably count and come up with 8. I know my double fact. So you can see that this tape diagram can be used for the 3 different unknowns. And the last one is coming up. There were some yellow beads. So these are yellow. Some means I don't know how many. And she put 14 beads. After she put some yellow beads were on Tamara's bracelet. After she put 14 purple, there were 18 total. Try to do that. Now I just switched to numbers. There will be kids switching to numbers by the end of this unit. They have the number sense to be able to do that. Or they write this with numbers and then they come down here and figure it out. So if I have 14, I need to get to 18, so that would be 14, 15, 16, 17, 18. So although I started with numbers to understand my question, I came down here and drew a representation of what was going on. And this would be blank plus 14 equals 18. Didn't know how many were there, but I can figure it out, and there were 4. And as they are able to manipulate these numbers in their heads, it will always require to see them to understand what the question is. Part of this is a habit of mind that we're teaching them. This is what mathematicians really do. And I guarantee you, by 4th and 5th grade, we are going to be giving them problems that they have to draw to remotely figure out what to do. When we get to, he spent half his time on a bus, got off the bus, spent a quarter of his time left walking, spent an 1/8 of his time in the store, and then got home after 2 minutes. You can work, the only way to work that out is to get a picture of it, or to work backwards. But that diagram will help you understand it. We understand in 1st and 2nd grade, numbers-wise, there are kids who can understand it. But we want them to demonstrate the understanding of the question, not just the numbers. Very end of the unit, we get to adding these oddball numbers below 40. So 15 plus 12. There are going to be 2 main ways. They're going to break apart 15 into 10 and 5, 12 into 10 and 2. They'll add the 2 10s together. And 5 plus 2 equals 7. And they'll know that that equals 27. What we will move on to is that you can hold one of those numbers as a whole. So I'm not going to break apart 15. I'm only going to break apart 12. But I can add 15, so now I'm using this. 15 plus 10 equals 25, and then add the 2 on. Does that make sense? Mm-hmm. We really do try to push to this. This is called partial sums. You break everything apart, you add it up by place value. It's just got a lot more steps than we need to do. Partitioning is where we hold one number. We usually hold the bigger number. I'll let kids experiment. It's going to work both ways, I guarantee. But why not hold the bigger one and break the smaller one apart? It becomes more efficient. So 17, I need to break apart the 14 into the 10 and the 4. 17 plus 10 is 27. 27 plus 4 is 31. I do want to talk about this step. Some kids might do 27 plus 3 equals 30 because they have trouble going across that decade, and then they'll do 30 plus 1 equals 31. So there's lots of ways to break numbers apart to make the addition accurate. So 19 plus 15. You can see that we chose to lock the 19. Broke this apart. 19 plus 10 is 29. 29 plus 5. Okay, I'm pretty good. I can do 34. I could have broken this into 1 and 4, and then 29 plus 1 equals 30, and 30 plus 4 equals 34.
But here would be easier to do 10 plus 10 and 9 plus 5.
You still got the problem with the 9 plus 5.
It's better than 19 plus 5.
To you. It's all stages, and what we really want them doing is making decisions on what works for them, not learning one strategy.
Okay.
Learning, like if you learn the strategy where you break it completely apart, when you learn the next strategy, you don't throw that one away. You make a decision which one to use based on the problem. So for you, you're saying, no, that would be easier for me. We want you making that decision. That really shows that you're thinking about the math and you're making an informed decision on how to solve it. But I agree with you, 9 plus 5 would be easier for kids than 19 plus 5. I think most kids would then get to 19 plus 5, break the 5 apart, and I think they would go down through this. They also may just add up. They might do 19, 20, 21, 22, 23, 24. That's fine. Our fingers are always with us. It's a little, I don't want kids to be embarrassed. That is a perfectly strong strategy at this point to get the right answer. Beyond 5, I think it gets messy. They might do adding 8 with their fingers, but what will happen is they've got to get the problem, they've got to have solved so much of the problem that we're down to just adding the last ones on. Okay, so 17 plus 23, we held that, broke that into 10 and 7. So I have 33 and 33 plus 7.
7 can be dissolved in 5 and 2.
I don't know that that would help us though. 3 plus 5, 3 plus 7, I don't know. I mean, at this point I do think kids could be adding on using their fingers. By the end of the year, we would hope that they would know, they should know their 10s. They should know 3 plus 7 equals 10. This is the hardest one though, because it equals 10. Oh, no. Do I have the right problem? Yeah, I do. And then they have to go to 40. They have to go that one up, and that's where we start losing them, and that's when we go back to pictures if they get lost there. By now, I would think that most of the kids know their 10 fat. Well, I shouldn't say that. They have till the end of the year to know their 10 facts. A lot of them are going to know them by now because we've spent half the year working with them. If your kids aren't, it's a little early, but by March or so, the teachers are going to start sending home games to play, like their websites that they could play them on. We don't do drill and kill flashcards. It's a great way to create anxiety. But for some reason, we can play a timed game where marbles blow up and it's fun. They get immediate correction in a non-threatening environment. Because even any of us, they shouldn't care, but they do. They want to be right in front of us. So somehow on the iPad, it's not nearly as embarrassing for them to make a mistake. And those games are built. They're all used to those games where you can make mistakes all the time and nothing really happens. Last thing I wanted to add on here. Oh, really last thing. This idea that 30 is 3 10s and 1 1, 2 10s, 10 1s, 1 10, 20 1s, and 30 1s. The reason I put this here is this is a game you can play in the car. That you can be looking at numbers on license plates and say, how many 10s are there? How many 1s are there? And see what sort of different numbers you get. Because really understanding that place value, I think this one is very easy to understand. I think this one is very easy to understand. And these are the ones we want to get them practicing with.
I just don't know how you can play it on the car.
Oh, it's just, you just grab a number that you see.
Okay.
Asking kids to
But
do a
it's
number that
5-digit
they're not seeing.
5-digit calculates.
Just take the last 2 digits, or let them pick. It's kind of let them pick whatever. It might be the speed limit on the way.
They pick numbers in traffic. I don't know from where to pick the numbers, but they...
Yeah, and if they pick the numbers, you kind of don't care. It's more the idea that they're taking a number and breaking it apart.
Because I thought maybe there's some game I don't know about.
Yeah, no. This is very, very low tech. Quickly, I have added 2 new sites on the back of here. Bedtime Math and Math Before Bed. You would think they could come up with 2 different names, 2 different groups. Excellent sites to go to that just have fun math. Ways to do, if we read a book every night, we really could be doing a little bit of math. And this is not tied to what they're doing in class. This is having open-ended conversations about math. I can't keep the 2 apart. One of them has these great pictures, and it's like, how many? Well, if I show this to you and say how many, 2, 4, you might say 16. You also could say, your littlest one could say 2 orange, or 4, no, it's actually 1 brown. There's a lot of ways you can answer that question. So it's just meant to be that fun, teasing way of math. And one of them does even have stories that are a bit mathematical. Those are 2, I highly recommend them. Math Playground, if your child is extremely loving math and wants to be challenged, instead of marching forward, go to the logic problems. They are fabulous. And that's a great way. That's what we don't overly cover in school. It's a great extension. Math Cats, really, it has everything to do with cats. If you've got a child who loves cats, I have a cat. I don't love it enough to go to this site, but they're fun. Huda Math just has some more. Dreambox is a paid-for program. It's aligned to the Common Core. It's not aligned to a grade level. You just start at the beginning and you just march through it. It gets the highest reviews I've ever seen of any website. Last one, Common Sense Media is simply a place you should be going any and every time your child wants something new. It's a nonprofit organization that reviews things with a parental lens. So they'll tell you whether it costs, they'll tell you what age range it's for, they'll talk about the maturity, they'll talk about whether there are ads placed inside the games, because that has just become incredibly big business, and a 6-year-old can't tell the difference. Upper age, I think really above 3rd to 4th grade, I don't care about ads. The younger kids don't know, and they are being sold stuff without us realizing it. That's a place where you can double check it. If you've got older kids, or as they get older, this is where you're really going to want to check the type of games they're playing and the books and the videos they want to watch, especially by the time you get to middle school, because they will swear it's okay. Videos, everything. Yeah, they do. It's about everything. It's just a really good website. Thank you very much. I think you can see, you understand this math.
Yeah.